Let's get started with the last day of the course. Yesterday, at the end of the day, we started talking about the something called kernel embedding. And basically today we are going to discuss several applications of embeddings. So kernel mean embedding was just a extension of the feature map. Oops. In particular, people tend to use the canonical feature map. Canonical feature map sends the elements in X to the corresponding section that are elements in H. And we saw that the natural way to extend this transformation to use distributions instead of just points was just by taking the expectation with respect to P of the sections. Right, so this is the kernel mean embedding, and we saw that it has some reproduction property in the sense that now if we do inner product with the mean embedding, we end up having the expectation of the function for any function in the kernel representative space. And this property might seem very fancy, but at the end is nothing more than the reproducing property. So the reproducing property says that this is f of x, and since the kernel mean embedding extends this linearly, just if you like by linearity of the inner product, we obtain this. Right? So we did a proof based on this representation, but at the end, having this result is a direct consequence of the reproducing property. Okay, so now let's start seeing how this kernel mean embedding can be used in 3 or 4 different applications, and that will be the end of the course. So the first thing that we are going to see is how to estimate these embeddings using data, using samples. So let's call it empirical. Okay, so now basically we don't know P. We only have samples from P. We have n samples that are IID samples from P, and we would like to estimate the embedding of P. We have n samples IID from P. We would like to estimate the embedding of P. And I guess in here there is a very natural estimator also, which might be thought as the plugin estimator, if you like. So the natural choice to estimate the embedding of P is, well, maybe the natural. So what would be the natural estimator of the embedding of P if we have n samples? What can we do to estimate the embedding of P if we just have n samples from P IID? How can it? We can estimate it using the sample mean. Yeah, right. Yeah. So the sample mean in here, right? So sample mean would be like doing the embedding of the empirical distribution, right? So if I have n samples, I have a very natural estimate of the distribution P, which is the empirical distribution. Empirical distribution, maybe some of you are not very familiar. Empirical distribution is just a distribution that is a discrete distribution in the sense that they only put mass in some specific sample. So the empirical distribution puts probability 1 over n in each of the samples that we have, and the rest of values of x have 0 probability. Right? So the natural estimate of the embedding is doing the embedding of the empirical distribution of Pn, and Pn is the empirical distribution. One way to represent it, simple way to represent it, although a little bit tricky if you want to be totally precise, is as a combination of delta functions, or if you like, as a combination of, so these are distributions that have probability 1 of being each of the samples and probability 0 for the other sample. Okay. So that's the empirical distribution. If we do the embedding of the empirical distribution, is very simple, right? So if we do the embedding of the empirical distribution, so we will be doing the expectation with respect to the empirical distribution of the section, right? But since the empirical distribution has 0 probability for all the x's, but for the specific x's that you have, and the probability of each x that you have is 1 over n, this expectation ends up being the sum of the sections divided by 1 over n. Other way to think about it is like the sample average of the section, if you like, right? So these steps are straightforward, but it is the first time that you see the empirical distribution. Might look a little bit complicated. Okay, so this is the embedding of the empirical distribution. So the plan is to approximate the embedding of the true distribution using this combination of sections. Obviously, this is one element in H. These are the type of functions that often appear, right? So we saw that the representative kernel Hilbert space can have more functions than this type of functions, but in most of the time at the end we are working with combinations of sections. Okay, so this is how we can approximate the true embedding using n samples. And now we are going to show a result that shows how good is that approximation. So today I'm going to keep calling the results theorems, but they are more like just corollaries of previous results. The proofs are going to be half a line, because of maybe 1 line or 2, because are going to be direct consequences of the things that we did. So here the result is going to be, well, we need that the kernel satisfies that boundedness condition. I think that's it. And then basically we will have this, and x1, x2, xn are IID samples from P. IID samples from P. Then with probability at least 1 minus delta, we have that the difference between the true embedding and the empirical embedding, let's say. So the difference between what we want to estimate and our estimate for it is going to be smaller or equal than 2 times M1 plus, let me see if I remember exactly. So basically these estimates are quite accurate. The accuracy in terms of the Hilbert norm decreases with the number of samples and depends on how confident we want to be about the bound in the usual way and also on this constant. So that's a nice result, and the proof is, well, as I said before, the proofs that now are going to be one line. I guess from the expression of this, you might already be guessing what we are going to do. So basically, the norm is the sum of over all functions that has a norm smaller or equal than 1, inner product of if so this is just right I don't know, the definition of the dual. So the dual norm of the Hilbert space is the norm in the Hilbert space. So we have that property, and then we can just use the reproducing property of the mean embeddings. So inner product of this, inner product is linear. So this is the inner product of F with the embedding of P, and the inner product of F with the embedding of Pn. So the inner product with the embedding of P is equal to the expectation with respect to P of F, right? This is just the reproducing property we wrote before. And the other thing is, okay, I'm going to write it. It's going to be the expectation with respect to Pn of F, right? I'm just using the reproducing property. Now, if we do the expectation with respect to the empirical distribution, right? Doing expectations with respect to the empirical distribution is the same as doing sample averages. Right? Again, empirical distribution only puts probability in the samples that we have, and each one has probability 1 over n. So the expectation becomes this. And now this sum of the true expectation minus averages when the functions are in the representation general space and have a bounded norm. We did it 3 days ago or something like this, right? So 3 days ago, we were bounding this based on the Rademacher complexity of things. Now the norm is 1, so that's why we have this expression. In general, we will have here the norm of the functions, but in here the norm is 1, so we get this, right? So this is, after this is just a consequence of the result 3 days ago. Okay, that bounded the differences between true expectations and probability. Okay, great. So then this shows that this is somehow easy to estimate embeddings of distributions. Just the natural estimator works quite well, and also is easy to measure the error that we will have when we use these estimators. Okay, so this is one simple thing. Let's keep going with some more applications of these ideas. The next thing we are going to discuss is something people call maximum mean discrepancy. Maximum mean discrepancy has been used in multiple techniques. For instance, maybe you have heard about this adversarial neural networks, generative adversarial networks. At least some of them use maximum mean discrepancies to do the level. We are not going to do anything related to that, but just for you to know that this maximum mean discrepancy has been used for many things. So let's start. Maximum mean discrepancy. Okay. I think yesterday I mentioned that once we can move right distributions into this nice Hilbert space, we can do many things because we have all the structure of the Hilbert space. So one of the simple things that we can do, well, I don't know if simple, but one of the things that we can do is to define a distance between pairs of distributions. As you might have seen at some point, there are many ways to define the differences between pairs of distributions, global labor divergence, and many others. So this is one specific type of way to describe difference between distributions. So call it like this: the maximum mean discrepancy between two distributions P and Q. P and Q are probability measures over X. Is just going to be, it's just going to be the norm of the difference between the embeddings. So this is very natural notion of distance between distributions, and this does not need to be an actual distance because this quantity can be zero for a distribution that might be different, right? So for instance, if we are using the polynomial kernel, this quantity will be zero as long as the distributions have the same moments. And so if we are using polynomials up to degree 10, these two things will be the same if the distributions have the same expectations of monomials up to degree 10. But if the kernel is rich enough, for instance, if the kernel is universal, I think I mentioned yesterday, if the kernel is universal, the embedding is an injective function, so that if the kernel is universal, this is an actual distance. This can only be zero if P is equal to Q. It's not totally necessary that the kernel is universal to have that the embedding is injective. Is enough if the kernel is characteristic. It's a slightly weaker notion than universal, but those things don't matter much for this course. So just to mention, like a Gaussian kernel and many kernels used in practice are universal and characteristic, and in those cases, this will be an actual distance. Okay, so this is one way to define it, but now you might be wondering why people call this maximum mean discrepancy. This will be like the distance measured in the Hilbert space, if you like, right, of embedding. And why the name maximum mean discrepancy? Well, because we can define it this way, or we can use these ideas and just say that this is the sum over F, where the F has norm smaller than 1, of the inner product between F and tau P minus tau Q, right? And that's the soup of the F. F is the smaller than 1 of, and now we use the reproducing property, and this is the expectation with respect to P of F minus the expectation with respect to Q of F. So we can define it just this way, or we can define it this other way, and this way to define it is maybe closer to the name it has, is the. So these are differences between doing expectations with respect to P and doing it with respect to Q for functions that are in the Hilbert space. So this measures the maximum difference between the means. If you do it with respect to P or you do it with respect to Q. Okay. In here, I am doing it like this. You might see in other places with an absolute value, as we talked the other day. Both things are the same because we are doing the soup over functions here. So if F is in here, minus F is also there. So this basically measures the worst case difference between doing expectations with respect to P or doing expectations with respect to Q, where the functions are in the Hilbert space and have no. Okay, good. So this is a maximum mean discrepancy. And now let's see how we can also measure this using samples. It's very similar to this type of result. And we can talk a little bit about one possible application of this distance.
Sorry.
Yeah.
Can you elaborate just this to the So P and Q are probability distributions. The F in the Hilbert space are determined by a kernel, right?
So H is a reproducing kernel Hilbert space given by some kernel.
Okay. So when you say, for example, that we use the Gaussian kernel, you also said kernel basis so that the Gaussian kernel can approximate a continuous distribution.
Right.
So you're saying that with the Gaussian kernel, this will tell us the difference in means between any given function or two any given distributions.
Well, but the function has to be normal.
Okay.
So yeah. Okay. So right. So this is good. So this is, I mean, So this so the norm is for functions that have a norm smaller than 1. For instance, if you think in the Gaussian case, right? So the norm basically was measuring the smoothness of the function. So if for instance, in the case of the Gaussian distribution, the norm was measuring the high frequency content of the function, right? So this in here is checking that, is showing that if the function is smooth enough, this basically describes the difference in expectation of functions that have that are smooth enough for this norm. Having said that, in here, right, as I think we did before, we can do it for functions with any norm just by dividing and multiplying. So if we consider B, so if we consider functions with a higher norm, what we have to do to recover that thing is multiply and divide by that norm, right? So if we know, so for instance, if we know the maximum mean discrepancy between two distributions, the difference of, okay, let me be specific. So the difference between the expectations of any function. So now the function is just a function in the Hilbert space, is going to be smaller or equal than the norm in the Hilbert space of that function times the maximum mean discrepancy. Okay. Just doing the same trick, right? So this is equal if I use functions of norm 1, but I can multiply and divide by the norm, whatever it is, and then we get this popping up, right? So basically, so I can quantify the difference in expectation of any function in my Hilbert space using the maximum mean discrepancy, but I also need to take into account what is the norm of that function. Yeah, that's a good point. Any other question, comment? Yes.
But in practice, you cannot know the norm of that function in the Hilbert space.
Well, I mean, yeah, I mean, depends. It depends on what kind of Hilbert space you are and how complicated is the function. For instance, if the function is a combination of sections, it's very easy to get the norm. In other cases, in order to know the norm, you might need to do very complicated integral or something, and then in other cases you might don't know. Yeah, so right, and depends also on the kernel, right? So maybe if the kernel is just a polynomial kernel or something, maybe you can do whatever you like. Yeah.
So the first equality in the general case is no the next one. Yes, the equality between the maximum mean discrepancy and that first definition with the supreme. That's in the general case, it is an inequality.
In the general case, what do you mean?
Without considering functions with norm smaller than 1 or equal to.
No, well, so in here I can. So okay, let's do it.
In the previous one.
So you mean
That's
in here?
yes.
So this is always an inequality, right? So in a Hilbert space, so I can, right? So the norm in a Hilbert space, I can always write it in this way. So in general, so if I have a norm, right? So if I have a norm and I computed this quantity here, that will give me the dual norm. But the dual norm of the thing I put here, right? But in a Hilbert space, the dual of the norm of the inner product is the same norm. So, right. Okay, good. So this is a maximum mean discrepancy. This is the definition. Two ways to see it. Now let's see how we can estimate this distance using samples. The idea will be very much like what we did before. So now we have n IID samples from P, and then we have some other samples from Q. Let's make it like this. The number of samples can be different. So now we have samples, some from P and some from Q. And I guess also the natural estimator of this distance would be just as we did before. We can do the embedding. We can estimate the embedding of P using the empirical embedding of the samples from P. We can estimate the embedding of Q using the empirical embedding of the samples from Q, and then measure the norm in H of that. And so the reasonable estimator, yeah, the reasonable estimator would be empirically estimate both embeddings and then just do the norm, and yeah, let's call this like the empirical estimate of the maximum mean discrepancy between P and Q, right? So this will be our estimate of the MND of P and Q when we have samples. Okay, so now this is something that we can actually compute very easily, right? Let's do it. So we can just do, well, so this is the norm in the Hilbert space, and then we can just use the definition of both empirical embeddings, and this is going to be the sections of the samples from P minus let's call it J, M, the sections corresponding to the samples from Q, and we do the inner product with itself, right? Everything. Okay. Right, and I do the square root because inner product with a vector and itself will give me the norm square, right? So this is just a straightforward writing down what the things are, and now we can just use the bilinearity of the inner product and have an expression like 1 square, and then the sum of xi with xj, I and j goes from 1 to n, and then in here we will have plus 1m square, and then the same I and j, but now they go until m, and k x I tilde xj tilde, and then we will have minus 2 times 1 n times n, and I and j, I goes to n and j goes to m, and then we have x I. So this is just using elementary properties of the inner product. So the estimate of this distance is something that we can very easily compute in practice as long as we know how to evaluate the kernel. Right? Just doing this operation. These things can also be written in matrix form, much more compact than this. If we define a matrix that has all the values of these quantities, but I'm not going to do it. Okay, so this will be our estimate of this distance, right? And then similarly as we did before, we can also measure how good is that estimate. Maybe before we do that, just a little comment. So this is a natural estimate of the distance, very simple. This estimate might be not the best one. This estimate might be not the best one. This estimate, for instance, is biased. Okay, so this estimate is biased, and the way to make it unbiased is to change a little bit the coefficients here, similar to what you would do to make unbiased the sample variance. And so modifying the coefficients a little bit you get an unbiased estimator of the distance. I'm not going to do it, but that's something you can find in most books. Okay, so for now we are going to use this estimator, and then
Can you give us the intuition of how you modify the coefficients, like to do that?
so it's similar to the way you modify the coefficient when you make unbiased the sample variance, right? So to make unbiased the sample variance, instead of when you do the averaging, instead of using the number of samples, you use how is one more than the number of
Less.
one less? Yeah, I know. Yeah. So in here is, I think, so in here basically you put something like n-1 square or something like this. I mean, I don't remember exactly how you change the coefficients. It's in the references in the course, the one that have a Kernel mean embedding, they have a specific expression to make it unbiased. It's not really that relevant to make it unbiased, because similarly to the sample variance for large enough n and m, it doesn't, so the bias is going to be very small anyway. Okay, good. So the result is what conditions I need now? Well, I guess the same as before, just that the kernel is bounded as before, and I think that's it. Then also with probability at least 1 minus delta. The difference between the two M and D, between B and Q, and then estimate, and this specific estimate here. This is smaller or equal than like this, 2m 1 plus square root of 5 logarithm 2 divided by delta square root of 1. So maybe let's talk a little bit first about the result, and then we prove it. So yeah, I guess this type of result now should be expected, right? Because this is basically measuring how accurate is the empirical estimate of the embedding. Since now we have two empirical estimates, one for the samples from P and one from the samples from Q, we have two terms. One decreases with the number of samples from P, the other one decreases with the number of samples from Q. And just a small detail, in the previous bound, I had 1 divided by delta here and 1 divided by delta. Now we have 2 divided by delta, because we need to have that two bounds have to simultaneously be valid. So we need to use the union bound, right? Okay. I'm going to do the steps now, but just to give an idea why this is what we should expect. Okay. Also, maybe before I do the proof, because otherwise it's maybe too boring, we can also talk how these things can be used, right? So one nice application of this type of this type of ideas is that we can do non-parametric hypothesis testing. For instance, if I have two sets of samples, right, and I want to know if they come from the same distribution or not, and usually in a university they teach you how to do these things, assuming like the samples are Gaussian or whatnot, and for that you have enough number of samples to use central limit arguments, and basically assume that the things are Gaussian, and then use the fact that the sample average are Gaussian or whatever, and then do the hypothesis test in this way. This is non-parametric in the sense that I don't need to assume anything about the distributions P and Q. If I use a universal or characteristic kernel, if both set of samples come from the same distribution, this thing here would be 0, and that would be an if and only if, right? So the only way the samples would come from the same distribution is that this thing is 0. And now this thing is something I can compute in practice, right? So if I want to have a hypothesis test that checks if they come from the same or from different distributions, I can compute this number. I can check how different it is from 0. If it's significantly different from 0, I can say that the distributions are different. If it's not, if the difference is not very large, I can say that I cannot I don't have enough information to reject the null hypothesis.
Sorry, I'm confused. You can compute the y hat and PQ, but you cannot compute the other side.
Right. But if you are trying to, so if you're, okay, let's be more specific. So basically, your null hypothesis is that P is equal to Q, and the alternative is that P is different to Q, right? So if your null hypothesis is true, this is 0, right? So you will reject the null hypothesis if this thing that you can quantify and 0 is big enough.
Okay.
Right?
Okay.
Yeah, of course, this you cannot compute, but yeah, if your null hypothesis is that they are the same. Okay, good. So this allows to do this non-parametric hypothesis test. Also, since we are talking about this, I want to mention that using this type of bound might be not the best way to do this hypothesis test. There are some maybe more useful results that measure the difference between these two things, like this difference for large enough number of samples follow Gaussian distribution. So you can do this type of test with slightly better than using this bound, but this could be a reasonable way to do in practice. Okay, so then maybe we can prove this and then we go for a coffee. Okay, so how to do this? Again, it's just going to be simple consequences of the things that we did before. So, of course, this is going to be the norm between the embedding of P and the embedding of Q, and this is going to be the norm between these two things. So, we can just use the triangular inequality. So the MND between P and Q, right? We want to relate it with the MND of the empirical embedding. So what we can do is if we add and subtract the embedding, empirical embeddings of the P's and the the ends, right? And then we use a triangular inequality. Right? So in here, I add and subtract the empirical embeddings of P and Q, and then I use triangular inequality, so that will be smaller or equal than the difference between the empirical embeddings and the distribution plus the one for Q plus the difference between the ends. This is just doing triangular inequality a couple of times. Right. So then we know that we can bound the difference between this. So this I can move to the other side. So this minus this is going to be bounded by this. Right. I can also do these things starting from here. Right. So if instead of starting from here and adding this, I put this in the left and add and subtract these quantities, I can have the same inequality, but with respect to this. So at the end of the day, I have that the absolute value between the distance and between these two things going to be smaller or equal than the using triangular inequality a couple of times. We have that and this is just this, right? So then we can use the result a few minutes ago that bounds this difference, right? And also this one. This is M, right? So now we can use the previous result to bound each one of these errors, let's say, and so that's why we want we get this expression, one corresponding to each term. As I said before, we want to bound the sum, so we want that the bound for each term is satisfied simultaneously. So that's why using the union bound, we have to put that 2 there instead of 1. Right more, I think here is not enough. Okay, so this is a maximum mean discrepancy. Yep.
I don't completely see why that argument of the union bound.
Okay. Right. So let's talk about the union bound a little bit. It's called union bound, but maybe it would be more accurate to call it the intersection bound. So basically, the probability of the union of two things is always going to be smaller than the probability of the sum of two things, right? So that's what give it the name, right? But in here, basically, what we want is that two events happen simultaneously, right? So we want that the probability of this bound to be valid, and also the probability that both this event and this event happens is bigger than 1 minus n, right? So basically, we want to ensure that the probability of the intersection of the, so we want to ensure that the probability that both bounds are satisfied at the same time, we want this to be bigger than 1 minus delta. Right? So that's our plan. Right? We want the result with 1 over delta. So then basically each one of the events have to happen with probability at least 1 minus 2 delta.
Okay.
Okay. Basically, people call it the union bound because if you have this bound for the union, you can also have a bound for the intersection, like how should I? So this thing is the same as this, and then this is 1 minus the probability of AC intersection on BC, right? And then basically the bound that you have for the union, you can transform it in a bound for intersections, changing the signs, and then the smaller becomes bigger, etc. Right? Maybe I'm not going to do the steps. So this argument of the union bound is something that it appears many times. So after you have seen it a couple of times, it's kind of automatic. Like if you want to have a confidence of 1 minus delta, and you need to have m events to be satisfied at the same time, to have that case, basically you need that each event happens with probability at least 1 minus m, 1 minus m divided by delta divided by m. So basically, so the idea is if I need that multiple events happen simultaneously, I need that the probability of each event to be bigger than before. And so basically in here, I need that each event happens with probability at least 1 minus delta divided by 2. And if instead of 2 events simultaneously, I need k events simultaneously, I would need each one of them happens with probability at least 1 minus delta divided by k. Okay, yeah. So this argument, union bound, happens all the time. Okay, very good. So yeah, if there are no more questions, maybe we can stop here and continue with a couple of more applications after coffee. Let's finish the course with a couple of short applications of these kernel mean embeddings, and then if you have some questions or comments about the course in general, we can also talk about it a little bit. Okay, so the next type of application, we can call it the density estimation. Yes, density estimation. And maybe kernel mean matching. As I said at the beginning of the course, there are many differences that people have done in machine learning using reproducing kernel figure spaces, and we are just going to describe a little bit a few type of applications. So for density estimation, also there are multiple types of ideas that people have explored. And now we are going to do some very specific case that I like to do it because it's related to something people call kernel mean matching. So the other day, I mentioned that this kernel mean embedding can give us a different interpretation to the usual kernel density estimation. Because if we choose a kernel that corresponds to probability distributions. The mean embedding of the empirical distribution would be another probability distribution, and then directly this could be used as an estimate of the distribution of the. So now we are going to do something slightly different, but somehow related. So maybe before I start, let's recall the setting. We have an IID samples from some distribution P, and in this case, we would like to estimate a P. We would like to have a distribution that is similar to P. One option was like choosing a reasonable kernel and then use as an estimate just the embedding of the empirical distribution. Now we are going to see something slightly different. So, as I mentioned before, a reasonable way to estimate the distribution from samples is always to use the empirical distribution, right? That is always reasonable, and in some cases is the right choice. In other cases, the empirical distribution is not that useful, maybe because the empirical distribution is different type of distribution, right? So let's make a picture. So we could have so the distribution of the random variable can be, I don't know, something like this, and then we have samples from it. So maybe some of them are here, and then maybe something like this, right? We have n samples, and they can be like this, right? And we want to estimate the distribution, and we have these samples. The estimate given by the empirical distribution is, as I mentioned before, is a distribution that puts probability 1 into the samples that we have and puts the probability 0 in all the other x's, right? So the empirical distribution will be this set of deltas, or whatever you want to call it. This will be Pn of x, right? So this way we will be approximating the distribution using this other distribution, and this approximation can be good in multiple things, like we can estimate expectations of the true distribution using this approximation accurately, but for other things is maybe not so useful because well, these distributions are itself pretty different, right? So this Pn is only supported in these specific points, and maybe we want to be able to estimate with something that is smoother, or in other cases, maybe we have many samples. So you can imagine that we might have 1 million samples. This approximation is determined by this 1 million samples, right? And maybe in some applications, if we might want to have a more compact representation of the approximation that depends on less parameters. Okay. So Pn is good for some things, not so good for others. So the idea here is to approximate the distribution P with some distribution P hat. So we are going to find a distribution P hat that is in some subset of distributions, and this subset is useful for some reason, maybe because these distributions are simple or are smooth, etc. Right? So the way we are going to find this distribution is by minimizing the distance in the Hilbert space with respect to the mean embedding. Okay. So this is one way to estimate the distribution of P using just samples. Basically, what we can do is we do the embedding of a Pn, and then we try to find what distribution has an embedding that is similar to the embedding of the empirical distribution. Okay, so that's the plan. As you can imagine, this type of optimization can be done efficiently only if the candidate distributions has some nice and tractable properties. Otherwise, it will be very hard to do the embedding, or maybe very hard to minimize this distance. But let's assume for now that we are able to minimize this, or at least to find a distribution for which this distance is small. Okay. So then the good thing of this type of distance estimate is that we can assess how good is the estimate in the following way. So this, I'm also going to call it the theorem, but it's also very simple. So also we have this bound for the kernel as before, and then the other assumption is that we have a distribution such that the difference with the empirical embedding is smaller than some value epsilon. Right. So this epsilon is something that, so if you are trying to do this optimization, right, when you do the optimization, you also know how good is the optimal value that you get. So this epsilon is something that you will have in practice. Right, if you can do with this, or at least if you can measure this norm, so then if we know that the distance between the empirical distribution, the empirical embedding, and the embedding of P is smaller than epsilon, then again with probability at least 1 minus delta, we will have that the difference between, so then we will have that for every function in the producing kernel space, the difference between doing expectation with respect to the true distribution and doing the expectation with respect to our density estimate of any function would be bounded by 2 times m times the norm of f, and then again the same type of things we always have. And then in here we will have the plus epsilon. So, okay. So this will be the result. This can be useful in practice, right? So this epsilon is something that we will have. This epsilon is something that we will have, at least if we are solving this optimization. After solving the optimization, we know what epsilon is. So then this bound, we will know how good is our density estimate, in the sense that we can bound how much the expectations are going to be different if we use the true, or if we use our density estimate. Okay, good. So the proof of this, I guess I'm going to do it because we have some time, but it's basically the same type of arguments that we have done multiple times. So very quickly. It's basically the same type of ideas as before. So the difference in expectations between f and between doing it with respect to p or doing it with respect to p hat is going to be, of course, smaller than. Well, I'm doing it for each f. So yeah, okay, let's do it like this. So this is going to be smaller than if we do this. Now I'm going to call it G so that I don't confuse you a lot. And now the norm of G to be smaller than the norm of the specific f. We are interested, right? So I'm going to do the proof for each specific f in H, right? So. And then and then this will be G tau E minus tau E hat, right? And then we use the same thing we did before. So basically we divide and multiply by the norm of f, and then we will have well, I'm not going to write it again. So if we do the same trick as before, we divide and multiply by the norm of f, we will have the soup over functions with norm 1, and that will give us the norm of tau p minus tau p hat. Right. Again, the same type of arguments as we have done always. And now, since the quantity that we can measure is this distance with respect to Pn, we do the same thing we did before. We add and subtract here the empirical embedding and use triangular inequality, and then we can write this. And now I'm realizing that I'm forgetting. The epsilon also has to be multiplied by f. So we add and subtract the empirical embedding, and we do the triangular inequality, and we get the difference between tau p and tau p n plus the difference between tau p n and tau p hat. I'm skipping a couple of steps, but all the steps we have done before several occasions are pretty simple. And now we are basically done. This thing we can bound with this probability this way. Okay. This is what we saw today at the beginning. And this other thing is the quantity that is smaller than epsilon. So we get that. Okay, so this is nice in the sense that sometimes when you estimate when you do a density estimation or something, you might have an approximation of the distribution, but sometimes it's difficult to measure how close how good is that estimate, right? So for instance, I mean, if you do like a kernel density estimator, you maybe minimize the Kullbaum-Leibler divergence. It would be maybe not straightforward to know how good are going to be my estimates in terms of expectations with respect to my approximation and with respect to the truth. Right? So this all tell us that if we use these approximations, the expectations I can carry with my approximate are going to be similar to the true expectations, and the difference will be bounded by that quantity. And this type of quantity is something that we can also assess in practice. We basically can know everything here. I mean, maybe not in every case, but at least in some cases. Okay, and now to make this maybe more interesting in practice, right? So in here I just said that, well, if you are able to do this optimization, if this subset of distributions is simple enough and so, right? So let's do a case in which you can actually do that optimization easily.
Sorry, for the theorem to hold, we don't need to actually solve that in minds.
Yeah.
It's for any we have that gives me that epsilon, right?
Right. So yeah, I think I mentioned that also briefly. I mean,
Yeah,
if you can go and get the best possible thing, is good. Maybe if this optimization is too complicated and you use some heuristic or something, is fine. This thing, I mean, if this is simple enough, this is something that you might be able to measure also. So yeah, as long as you have a bound for this, you could have this other type of bounds. Okay, good. So now let's see a case in which you can actually do the optimization, and that will link to the next and final application. So one case in which you can actually do it is if you want to approximate the distribution using simple distribution given by, should I call it M? Okay, let's do it with K. So let's imagine that well, you want to approximate the distribution using very simple distribution similar to the empirical, but instead of having n support points, we are going to have k support points, and instead of being the probability of each one just one, we can have different probabilities. And these samples might be different to the samples that we originally have. Right. So this type of approximation could be useful, for instance, if n is very large. Yeah, the example I mentioned before, right? So if you have 1 trillion of samples, you don't want to keep all of them every time. So so if you use the empirical, every time you want to do an estimate, or every time you want to use that approximation for something, you will need to use the 1 million samples, right? So if you approximate the distribution with this type of approximate, and maybe k now is, I don't know, 100 or something like that, then you will only need to keep these 100 samples. Well, I don't know if it's samples, these 100 x's, and every time you wanted to do a expectation or something, you will only need to use these 100 samples. Okay, so that can be useful in those type of applications. How you would get this x tilde I'm writing there? I guess you could do something simple, like maybe some clustering of the original x's, something. So, okay, so if we approximate if we try to approximate with a distribution like this, then this is very tractable type of problem, because then the optimization. So this distribution, let's imagine that the xi's I found it or I decided which xi's to use before, like doing this clustering and so on. So this optimization will be only optimization with respect to these k betas. And the optimization will be, well, going to write it, will be the empirical embedding minus the embedding of this pi hat, and this is something that can be done easily. Let's do the optimization with the square, so we avoid the square roots. Of course, it doesn't matter, right? Because this is increasing because these are positive numbers. So then this will be the inner product between the empirical embedding of this minus the embedding of this distribution is going to be beta j, j1 to k, k, x, j, tilde, right? And then again, same thing. Okay, and then just doing the usual operations, we will get something similar to what I wrote before. Right, and what else I'm missing? Yeah, minus 2 times n sum beta I k k with I j x I x beta j x I x tilde. So this is just again using the very simple properties of the sections and so on, right? So basically doing this optimization, we'll be doing the optimization here. In terms of the betas, this optimization problem is quite tractable. It's going to be a quadratic optimization problem. Well, I forgot to mention, right? But I mean, in order for this to be a reasonable, I mean, to be a probability distribution, we need that the betas have to be positive numbers, and also the betas have to add 1. Right. Otherwise, this p hat is not a distribution, right? So we will have a quadratic optimization problem with the constraints that the variables have to be positive and they will need to add to 1. But that's easy to solve with the usual methods for convex optimization, right? Okay, so at least in this case, we can actually do everything. Okay. Good. So this type of application is an example of these ideas of kernel min matching. So basically in here, what we are doing is we want to find something. In this case, we want to find this distribution, or we want to find these betas in a way that the mean embedding match. Right? So we want to find these weights for this distribution such that when we do the embeddings of this distribution and this distribution, the embeddings are as similar as possible. Right? So we want to match the mean embeddings. Right? This is one way to use these ideas. And now to finish, we are going to discuss another application of very similar items. Okay, questions before we go with the last thing? Okay, so the last application is using this kernel min matching for a problem that is known as a covariate shift. The covariate shift. So when I describe the supervised learning problem formulation, we were talking about the fact that we can actually learn because the examples are training follow the same distributions as the samples are tested, right? And I mentioned that that's the most usual case, but it's not totally necessary. sometimes, I mean, in practice, always the distributions at training are going to be at least slightly different than the distributions at test because things change. There are many techniques that are also developed for cases in which the distributions at training are different to the distributions at test. And as I said before, they cannot be any kind of difference. We need to have some idea of how different they are. So this cognitive shift is one specific case of a type of difference between the distribution at training and the distribution at test. So let's describe the problem here. So as before, we want to find a classification rule for a function from x to y, from x to r, such that the expected loss is small. Of course, what we want to make small is the expected loss when we go and use it and use the rule, right? So we want to make small the expected loss over the distribution at test, right? The distribution that we have when we actually deploy the rule, right? So we want this to be small, and PTE is going to be a distribution of x and y. So we want this, and we have training samples just as before. But now what happens is that the training samples are again IID, but now they come from a different distribution, PTR. So we want to make this small for some distribution PTE, but the samples that we have are from a different distribution. In the standard supervised classification, both distributions are the same, but now the two distributions are going to be different. Okay, and as I said, they cannot be just different. We need to have some idea of how is the difference. And in here, what happens is that so these two distributions are distributions over both x and y, right? So we have pairs of x and y's, and then in here, what happens is that the marginal over x at training and at test is different, but the conditional of y given x is the same at training and test. So the distributions are different, but not totally different. At least the conditional is the same. Okay, and now let's see what this difference would mean and so on. So, so only the marginal in x is different. So let's make a picture of this type of situation. So let's imagine that we are in a case in which we have very simple x's just in R2, and then the positive examples are in this area. Okay. The positive samples are in this area, and the negatives are in all other places, right? Just simple example. And then, okay, so this is if we have samples everywhere, right? But maybe a training, let's imagine that a training, we only see examples here. At training, we only see examples in this area, and then at test, we are only going to try to predict examples in here. So this is these kind of situations are common in practice, right? So you can imagine, for instance, an example like this might be. So you might be developing a pharmaceutical drug, right? And then you want to know if the drug that you are developing is going to help people or not, right? Or of some type of population, right? Maybe let's imagine that this is a drug that you use when people have some illness, and that illness usually happens in elderly people or whatever, right? And then the data that you have to see if that drug is useful or not, maybe data corresponding to volunteers to the study, and maybe the people that volunteer to the study, some of them have the same characteristics as the people in which you are going to use the drug later, but maybe some others have different characteristics. Maybe younger people also volunteer for this study, etc. Right. Okay, so if you are in a situation, of course, in here, the fact that the label for 1x is positive or negative, it doesn't matter, right? So the only difference is the same in test and training. The only difference is that in training you sample in this area, but in test you are only going to see samples in this area. Okay, so if you are in a situation like this, and you try to use the standard supervised learning approach at training, the samples that you have at training will be maybe something like this. Minus, minus, and then plus, 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 plus. Right. So if you are in a situation like this, and these are the training samples that you have, okay, maybe I shouldn't. Okay, let's pick another. Hold on. So if you have these training samples and you run your algorithm for supervised classification, it's very likely that you will end up finding this classification rule that classifies one side as plus and the other side as minus. Right? At least if you are in a situation even when you, right? So this is basically your classification rule will set to the right plus, to the left minus. But this classification rule will be pretty bad, right? Because when we try to use it, we are going to see only examples here, right? So if the only examples that you are going to see are going to be in this region, there a classification rule. This classification rule that you learn at training is going to be pretty bad, right? Because basically you will classify all the examples as positive. So, okay. Of course, I'm exaggerating the example to make the point. In practice, things are not that bad, but it can be very bad, right? Okay, so that's the problem. And how to solve it? So, okay, in order to solve it for this type of problems, it's common to have some more information. So basically, at training, you have samples from the training distribution, and also you have some other samples from the test distribution, but for the test distribution, the samples are unlabeled. So those come from, so those are IID from the test distribution, and they are unlabeled. So in this case, to make things easier, you can also have access to samples here. So this could be like in practice, this will be like, okay, this is the results. So these are the results I get in my trials with the volunteers, and then somebody tell us that usually the people that use this drug are people with are people of this type. These are examples of people that is expected that they are going to use this drug, but for these guys, you don't know if the drug was effective or not. You just know how are this type of people. Okay? So this is also very reasonable in practice to have these samples together with each other. And then basically the idea is to use these training samples and these unlabeled samples to find a rule that is good at test. Okay. So that's the problem we want to solve now. So any questions about the problem or so? So okay, so the usual way to solve it, usual method. So the usual method is called reweighting or something like this. Reweighting. So basically the idea is, I want to make these expectations small. I have examples from this other distribution. One thing that I can do is to use the fact that the expectation at the test of my loss is going to be the same as doing expectation at training, but weighted using the marginal at test on training. I'm doing it right? Yeah, I think so. Okay. Okay, so basically this is because, well, this expectation here is the integral over test distribution of that function over x and y, dx and dy. And then if the support of the train distribution contains the support of the test distribution, so in here, at least if that regularity condition is satisfied, then we can rewrite this as PTR x y. Should I? Okay, let's do it in a couple of steps. So, okay, so then I will put this asterisk later. So this is just, we can decompose the joint distribution as conditional times the marginal. In here, I just decompose the joint. Now, this thing is the same in training and in test. And if I want to write it, as an expectation at training, I can multiply and divide by the distribution at training, and the asterisk before means that I'm allowed to do this as long as this is not zero. If this is zero, this also has to be zero, right? Otherwise, this is not true, right? So basically, the support of the places in which these are non-zero have to contain the places in which this is non-zero. That's also why in the picture I put before, I put the distribution of V contained in the distribution of PTR. All right, so well, if you have this equality, reasonable way to go about this problem is to try to minimize, right? So we have training examples, so we will use the training examples, and then what we are going to minimize is the average loss. Should I? Yeah, this is fine. Well, this over 1 over n, it doesn't really matter. So we can use the same approach as before, but now we are going to weight the samples based on the ratio between the margin. This is also very, very clear that this is something reasonable to do, right? So basically, I have a bunch of training examples. I removed the. Okay, so let me put the example again. So I have my training examples are like this. My training examples are like this. And if I use all of them, I'm going to choose this rule. But now, if I give a small weight to the examples that are in this area, but a much bigger weight to the examples that are here, right? So if now the examples that have higher weight are these ones, I will find the right hand. Right, and that's basically the idea there. Okay. So how to do this? So this is what we have, right? So what we have are these training samples are these other samples, right? So of course, if you know the marginals, you just go ahead and do that optimization. But in practice, often you only have samples, right? So if you want to do this type of approach, you will need to somehow obtain these weights, right? Or estimate that weights. So the naive approach will be like, well, I have samples of the x's for TR, and I also have samples for the x's for TE. I could use those samples. So I could use the n samples from TE to get an estimate of these are from TR, to get an estimate of the marginal of TR, and I can use the samples from TE to get an estimate of the marginal at test. So this is the naive approach. I can use the samples that I have, I get the estimates, and now I can estimate that weight just doing the ratios between both density estimates. This is one way to go about it. You have some algorithm that is able to do these estimates somehow, and then you could use those estimates to approximate the ratios. So this is a naive approach in the sense that we can do better than this. Okay, yes, let's talk a little bit about this. So why do you think this is not the best type of approach, or how this can be improved? Anybody has an idea? Or maybe, I mean, who thinks that this is the right way to do and just focus on this? Or why this is suboptimal? Or why this is... Maybe Jose, no, you.
I mean, I can say.
Yeah, but maybe you don't. Has worked on this. So okay, so why this approach is not the best possible idea? So, like some days ago, we talked a little bit about this book of Babnik and ideas of Babnik, right? So one of the things that he says that is that if you want to solve a problem, try to avoid solving a harder problem as an intermediate step. Right? And these kind of ideas are very important in machine learning, right? So, in here, what we are trying to do is to find the weights for this sample, right? So we try to find some weights to make this. So we try to find these weights. One way to find those weights is by first doing density estimation and using the density estimates to approximate the weights, right? Well, finding the density estimates can be very hard. And even if this, so why is harder to find the density estimates than finding the W's? That's maybe better way to put it. So why is it harder this step than finding the W's? Even if you don't know anything about density estimation. So it's harder basically because, I mean, if I am able to solve this problem, so solving this problem implies that I can also find the weights, right? So if I am able to solve this problem, as a consequence, I am also able to find the weights, right? So solving this implies being able to find the weights, right? But the other way around is not necessarily true. Right? So I might be able to find the weights without first finding this, estimating these marginals. So basically, finding these marginals is at least as hard as finding the weights. Right. So, okay. So let's try to find the weights directly. Right. So let's try to find the weights directly. And that's basically, so we are going to try to find the weights directly using these ideas of kernel min matching. So basically, what we want is to find some weights such that doing expectations at test is the same as doing weighted expectations at training, right? So based on the things that we said before, reasonable thing to do. Should I write it? Yeah, I think we don't have notation for the other case. So something. Okay, so maybe yeah. Since we have a couple of minutes, let's see if we do it together. And so based on the kernel min matching ideas I mentioned before, was the reasonable approach to directly find the weights. We want the weights. So we want the weights that make us approximate expectations with the training samples, approximate expectations of the test samples. Well, so we will. So if we are going to do it based on kernel min matching, basically we are going to try to find weights. How many? N. So we need one weight for each training sample, and we want to find the weights such that we match the embedding of two things, right? So, and basically we want the weights such that doing expectation at test is the same as doing expectation at training. And we only have training samples and test samples. So what kind of embeddings should we try to match? Right. Anybody? Some ideas? Right. So basically, yeah, I think it should be enough, right? So we want to find the W such that when we compute expectations at test, we get very similar to expectation at training, and we are going to match the embedding. So if we want both expectations to be very similar, we will try to match the embedding of the empirical of the training and the embedding of the empirical embedding of the samples at test. So we have, okay, so we will try to match, let's put it like this. So we have m samples at the test. So we will try to match the embedding of the m samples at the test with the embedding of the n samples at training, but we will weight the averages are trained by these W's. So what we want to match will be the, I'm doing it, yeah. Yeah, it's without the. So we will, instead of weighting all the training samples with 1/n, we are going to weight it with the W's. So we want to match these two embeddings. Yes. So we want that the doing expectations with examples at test is very similar to doing the expectations with the samples at training if we weight it in the right way. Right? So we are trying to find the weights such that this quantity is as small as possible. Right? Just as before, we found the betas, right, by matching the embedding of the empirical and the embedding of the other distribution, right? So it's
Then you have to remove the 1/n.
Yeah. So I thought when I wrote it, I mean, here in optimization, of course, it doesn't matter because it's just a constant, but then to have it, right? So, okay, to have it exactly the same, right? So this is basically same kind of thing we did before for density estimation, but now this is trying to find the weight such that expectations at training match expectations at test. And then once we have these W's, we can just use the usual empirical disminimization and so on. Of course, this is the same as doing with the square. And also, well, since these are going to be weights, they will also be positive and they will also adhere to 1. And basically, it's a same type of optimization problem as we saw before for density estimation. And this is something that can be solved easily with the usual solvers or usual techniques. And once we have the weights, we will plug the weights here and just run the usual empirical disminimization, but weighted. Notice that with this approach in here, we are finding the weights, but we have no idea what is the marginal of the X and the marginal of the marginal at and marginal test. So we skip this step and we direct 3. Okay. So before we were saying that if you have a solution for if you have a way to estimate the marginals, you can estimate the weights. Now we have a method that finds the weight without finding the margins. So this should be more reasonable.
No, I get it, but why not solve both at the same time? Would it be possible?
Well, I mean, for this, right? If you are just doing a coverage shift adaptation, that's the only thing that you care. Right?
Okay.
If that's the only thing that you care, the only thing that you care is the W. So I'm not saying that it's useless to estimate the marginals. In other cases, you might want to do both things.
No. I'm saying with that minimization on the left, you get the weights that match covariance shift, right?
With the
With the minimization you have right there on the left, no,
here, yeah,
you get the weights that
right.
Matching of the covariance.
Right.
And then you take them and plug them in that other minimization over F, right?
Right. So basically, you take these W's, you put it here,
Yes. And solve another problem.
and solve the here. Yeah.
Yes. So my question is, if you can do them together, right?
Yeah. So this optimization and yeah. Okay. So you are asking like going a step forward,
Yes,
right?
yes,
So what about if we try to
F over the W that, yeah.
if we try just to adapt to covariance shift without doing in the intermediate step of finding the weights? That would be great. I don't know how to do that. I don't think that people know how to do it. Yeah, I mean that would be So basically, that's the right kind of thinking and this for machine learning. Right? So if you want to do one thing, if possible, try just to do that thing. Not the first do something else and then if possible. I mean, right? So that's what Barney says. Right? So if you can avoid to solve an intermediate, I mean, if the intermediate problems are not harder than the final problem, is fine to do it, right? But it's important to try to avoid intermediate problems that might be harder than what you really want to do. Okay, so any other question, comment about this or about the course in general? What if that's questions or comments? So if there is no questions or comments, maybe we can just stop here. So thank you very much